All right, boys and girls, welcome back to the drive-through. 14.3, moving up in the world, and we can see the end, which is 14.8, okay? So this is nice because 14.3 is way more manageable than 14.1 and 14.2. 14.1 and 14.2 combined a lot of new topics with a lot of old topics that were difficult to understand, like parametricizing a path and all sorts of things that were tricky. If you can understand these four bulleted points right here, then I think you're going to find this to be a really fascinating lesson, something that you can really understand. So, what does it mean for a function, a force field, okay, to be conservative? Remember when Mr. G came in here and dropped those paper clips? What did that physically mean, Lex?
The sum of the potential and kinetic energy is the same at every point.
That's right. Excellent. At all points in the field, the sum of the potential energies is the same as the sum of the kinetic energies through a path. Okay? Remember that?
I just don't understand how you calculate potential energy in like a field. Like, sure.
Okay, so now how do we show that a two-dimensional field is conservative?
Take I in respect to dy, take j in respect to gx.
Excellent. This is the notation we've been using. Oh, yeah, sorry. Okay? That's how we've done it in two dimensions. Show that the partial derivative of the x function in terms of y, or with respect to y, is equal to the partial derivative of the y function with respect to x. If those two things are equal, then we set it to be conservative. How do we show that a 3D function is conservative? Its curl is 0. Excellent. And we'll talk about that a little later, okay? What's another way to show that either one of them are conservative? Just demonstrate that they were born out of some potential function. Find that potential function. Okay, that's going to be the key to understanding this section. And we'll tie that in, sorry, we're missing a Y there. We'll tie that into this fundamental theorem of calculus. So let's start with that. Does anyone remember what the fundamental theorem of calculus actually tells us? Okay, good. Okay, let's write it out. So, if we've got some f of x, okay? And we'll just leave it like this. If capital F of x is equal to the integral of f of x dx, okay, then the integral from a to b, okay, of f of x dx is equal to what? Capital F of b minus capital F of a. Okay? Now, I've always kind of just thought like, well, that's just saying that the integral of a function, or the integral of a derivative is the function. But that's actually not what it's telling us. And this also kind of just looks like how to do an integral, does it not? That's how I've always interpreted it. Like, this is how you do an integral. But yesterday it dawned on me, only from getting prepared to teach this lesson, that it's actually telling us more than that. So, what's that? Okay? It's b squared minus a squared, right? Isn't that the answer to that? Well, look, check that out. So there's our function, okay? What does this shaded area represent? That's the integral from a to b of 2x dx. We're just kind of going back over what we just did. But here's, to me, where I was like, oh, seriously? Like, that's what that is? What do we have there? That's capital F of x, right? Which is x squared. Here's what's crazy to me. This area, this black area, is this point minus this point. So we're finding the area of a region by subtracting out the values at 2 points. That's going to be the key to understanding today's lesson, okay? And what we're going to end up doing is kind of ingenious. It's the ultimate exercise of intelligent laziness, which is math, okay? So we're going to start with an example. So we're going to find the work done here. I'll pause this. Okay, so what we're going to show here is that the work done in a conservative field through a given path is independent of the path. What does that mean? That's exactly right. It does not matter the path it takes to get from A to B. The work will not change no matter how you get from A to B. We're just going to show that here. This isn't a proof. It's just a demonstration. But what should we do before we start going on this? We should show that this thing's conservative real quick, okay? So this here is our M. This is our N. What is dm dy? 1/2 x. And what is our dn dx? And so now we've shown that it's conservative, okay? So we struggled on this a little bit on the quiz, and you'll get your quizzes back tomorrow, maybe even at the end of the bell today, okay? No, it'll be tomorrow. It'll be tomorrow. Give me the parametric equation for this. It's the easy one. X equals? So y equals? So dr is 1, 1 dt. What that means is that r of t is t comma t. Okay? So the integral of f dot dr, the line integral, is the integral as t goes from what? 0 to 1, right? Oh, shoot. No, you don't know that. Along the path from... I forgot to fill in that important information. 0, 0 to 1, 1. So now that I've written that up there, do these limits make sense for you guys? Okay? So it's f. Well, our f is 1/2 t, comma 1/4 t squared dot with 1, 1 dt. You follow that? So that's the integral from 0 to 1 of 1/2 t squared plus 1/4 t squared dt. The integral from 0 to 1 of 3/4 t squared dt, which is 1/4 1/4 t cubed from 0 to 1, right? 3t cubed over 12, if you will. And so that gives you 1/4. That's our work. So far, so good? Okay, now a little tougher now, and like I said, we struggled with this on our quiz. So somebody give me the parametrics for our second curve. I don't think that would work. No, it could be, but it's not that hard. There you go. Make sure you know that's a y. That's the easiest way. Another easy way would be x equals t, y equals radical t. Okay? They both work. Remember, you might have to change your values on your integral, but here t goes from 0 to 1 again. Okay, so what is, well, r of t is what? T comma t squared. Okay? T squared comma t, thank you. Alright, so dr equals 2t comma 1 dt. So we are going to do, I'll skip down here, the integral from 0 to 1 of, okay, 1/2 xy, 1/2 t squared times t, comma, 1/2 x to the x squared, or sorry, 1/4 t squared squared, dotted with 2t comma 1 dt. You guys okay with that? So you get the integral from 0 to 1 of 1/2, nope, of t to the 4th, right? Plus 1/4 t to the 4th dt. Just stop me when I make a mistake. That's 5/4 t to the 4th dt. So it is t to the 5th over 5 times 4. It's that. From 0 to 1. So it's 1/4. So what have we just shown? That's right. Thank you, Ted. In the first one, our path went from here to here, and the work was what? 1/4. In the second one, our path was like this, and the work done was 1/4. We're to save some time on the video. What's the path look like in the third one? It's kind of a little bit, well, it's a little different, but it's kind of the opposite of the second one. And let me just tell you, and I hope that you trust me, that you get a 4th. Okay? So, one concept about independence of path that's really important is that if you now have a, whoops, if you have a path that's like this, okay, that's a combination of 3 smooth curves, and let's say it's going in this orientation. What's an alternative path to get from where we started to where we ended? Not going anywhere, right? This is called a closed path. Maybe you're familiar with that from your programming terms. What's the work? That's right. Okay? Always. Because it's like taking a path of 0. So far, so good? Okay, well here's where the fundamental theorem of line integrals comes in. And if you understand the fundamental theorem of calculus, then this will help you tremendously. Here's the hard part. Now our capital F's and lowercase f's have been switched. So bear with me here. This is literally my only role here is to help you with the notation. Okay, you can do all the math. It's the notation that's tricky. What has this thing been representing in our class? It's a force field. If this force field is conservative, then what is it the result of? It was the gradient of something. Do you remember that? If this exists, then it's conservative. Well, think about what we just said with the fundamental theorem of calculus. First of all, last bell it went great because someone was like, oh, this is going to be awesome because we're going to take these complex paths and instead of integrating over a complex path, what do you think we're going to be doing today? Making it a simple path. We're actually going to do even better than that. Okay? Here's what we're going to learn. The line integral of f dot dr, so this is just work, but it can represent more than work. You need to understand that. It can represent so much more than just work. Okay? That's the same thing. Do you remember that? Just look from above. We found this force field by taking the gradient of some function. Okay, so far so good? Well, all we're going to do is and this is where the notation gets kind of hard, f of x of b, comma, y of b, comma, z of b, minus f of x of a, comma, y of a, comma, z of a. Okay, let's go backwards. This is today's lesson right here. We're not going to simplify the path. What are we actually going to do? We're going to find the parent function and just pop in the points. That's all we're going to do. Okay? It makes it so much easier on us. Ted? Well, we're going to have to show that it's conservative, or we might waste some time. Because if we do this, and it's not conservative, we're going to get the answer wrong. But we can't do it. We can't find a parent function if it's not conservative. So the debate that we're going to have when we do our example is, what's faster? Finding out that it's conservative, or just trying to find the parent function first? And that's going to be up to you guys, okay? I'm going to prove that it's conservative before I do things just because that's the logical order of my brain. Okay, so we've got some force field defined by these functions, and you've got a path C that's funky, okay? It's traveling from 1, 1, 0 to 0, 2, 3. So, first, let's see if this thing's conservative by finding its curl. Okay, what do we need the curl to be to have it be conservative? It needs to be 0. So here we go, I, j, k. We got derivative with respect to x, derivative with respect to y, and with respect to z. And then you got 2xy, x squared plus z squared, and 2zy. All right, so what is the curl? Well, it's the derivative of this with respect to y. So 2z minus the derivative of this with respect to z, 2z. Well, good, that's 0. Minus the derivative of this with respect to x, 0. That says 2zy. Okay, sorry. Look at over here if it helps you. Minus the derivative of this with respect to z, 0. So far, so good. And then plus the derivative of this with respect, the derivative of this with respect to x, the derivative of this with respect to y, and what do you get? 2x. And what do you get? You get 0. So curl equals 0. Therefore, it's conservative. What's our next step? Find a potential function. So we need to integrate 2xy with respect to what? And what do you get? Plus some function of y and z. Okay? Let's integrate x squared plus z squared with respect to y. That's not 0. What is it? X squared y plus z squared y. And for this one, it actually helps you more to not factor out that y. Okay? Plus what? Plus some function of x and z. Okay? And then we're going to integrate 2zy with respect to z. And what do you get for that? Z squared y plus some function of x and y. So can you use all that information to piece together our parent function? X squared y plus z squared y plus some constant. Okay? Why do we use k? I think it's the multivariable version of c. It's like we're so much smarter than c. We're k constant. Okay? All right. So we found our parent function. Now what comes next? Plug in the point and use the fundamental theorem of line integrals. What about the k, though? The k is going to subtract out. Okay? So now I'm just going to do f of 0, 2, 3 minus f of 1, 1, 0. This is 18. That's an 18. Minus 1. And so the work equals 17. And all I want you to know is at the end we didn't do any magic, but we did math magic, I guess. We just did this. Instead of finding the area under the curve, we just took f of b minus f of a because it was easier. Not because we had to, because it was easier for us to do it that way. And that way we didn't have to do any of that parametrization or things like that. Okay? You good with that? Boom!